North magnet approaching a red coil, and a north magnet approaching red coil, a north magnet leaving a red coil, one centered down here, red to red. And as you go the other way, up the other side, they're working against themselves. One is generating clockwise energy, and one's generating counterclockwise energy. And these things are all wired in a series. All the red coils are strung end to end like lights on a Christmas tree. So you're losing some of the electricity because it's going back and forth between the coils. It's not coming out the other end. And I found a solution for that, believe it or not. Down here, you notice at the bottom where I got, well, it's clockwise, counterclockwise, clockwise, counterclockwise, clockwise, and then another clockwise. And that leaves you two counterclockwise 180 apart. And what this does for you is, if you notice that all the coils coming down this side are generating electricity out of the stator. It's making electricity to charge your batteries. Over here, about from there up, they're not making electricity. They're taking away electricity. You've generated it, but you've run it from one coil back to the other coil, because that's happening before it comes out up here. If we're saying that these two coils are the end of the strings, you know. But when I jump it ahead, it's just like when I started up here. If it's all working for me around in here someplace, and I jump it ahead one, I'm just starting the same thing. I'm starting with a clockwise and turning 180 degrees of coils. Down here, I'm starting with a clockwise, turning 180 degrees of coils. If you was to put this together like I'm doing mine with a split stator, so you can take out the left half and the right half, easy to assemble, easy to do maintenance. Don't lose your clearance on your magnets. You're trying to scrub on things. Once you get it set, you really don't want to mess with that. If you don't like it, you take this thing and you flip it over. You put your counterclockwise back here where it was. So if you want to test this, make a two-piece stator, put the bus bars on it, and if it doesn't do what you think it's supposed to do, you haven't lost any money. Just flip the thing over and bolt it back in there. Make a regular pattern where the stator bolts to the mount. The stator bolts down outside of the magnet wheel. The bolts have to clear the magnet wheel. They can't be anywhere else. If you put them in the middle, you put your bottom magnet wheel, and you bolt it to something somehow. I'm not sure how you do that, because the magnet wheel generally is a solid piece across to the axle. Either you got spokes or you got a solid plate. I don't see you bolting it in there. Bolting it onto the center doesn't work because the shaft is turning with the magnets. There's nothing to bolt it to inside. It's going to be bolted on the outside just by default. So just make a regular bolt spacing around there. And if you don't like this idea, flip it over. Won't cost you anything. Okay. There are a lot of ways that you can connect coils. The easiest is hook it up in three-phase. You buy a three-phase rectifier to turn it into DC. And that won't work to make an AC welder into DC. I've tried that. because it switches internally, and sometimes things are positive and some things are negative. It's what's the one you can use? Well, I tell you, if you buy a three-phase bridge, it works, no problem. You can get it for any kind of number of amps you want, because people are using them in small quantities. Stuff, the price is kind of high for what you get. It might be $18 or $20 when it really should be $2. But you know, it's as a percentage of your project, it's not that much. Other ways to do it. Back in high school, you remember the Wheatstone bridge? It's 4 diodes. The top 2 pointed up and the bottom 2 pointed down. And it's a diamond. You have the 2 wires on either side comes out DC, and the 2 wires top to bottom coming in is AC. So it either comes in, goes out this way, or it comes in, sucks milk, and goes out that way. And the other, like the negative, does the same thing on the other side. So it's the output is not linear because it's basically a sine wave. So it's sort of a rough, choppy kind of current. But you can get these things. I buy them for electric brakes on cranes. They used to have these big, bulky pieces that weigh 4 or 5 pounds a piece, and they had silicone mica and stuff like that in them, and people jarring things with the crane and running one crane in another. First thing happens is that thing quits and the brake won't release. It takes electric to turn the brake off, not turn it on. And then you try to find those things. They've been out of production for 10 years. So I bought some of these little solid state potted things. They're about 2% the volume of what I took out. I had an enclosure 12 by 18, 6 inches deep. And I put this little block in there, and it was 1.5 inches square and 3/8 of an inch thick. And these big spade connector things on the top. But I put connectors on the wires and plugged up. And 6, 7 years later, it was still working like what was put up there. But those things were cheap. You can get them for under 40 or 50 cents. There's nothing saying you can't hook 2 coils in series and run them through one of those. Or have one on every coil, because not everybody's running 30 coils. I'm running the coils because my fan is 21 feet across. That's why I got a pretty good size ring on it. Also, metal's expensive over here, and I found some 120 tooth RC40 demountable sprockets, and they had like an E hub in them, so I don't know, I can put a 3 7/16 shaft. So there's no problem at all putting a 1 15 shaft in the thing. And actually, the turbine itself is on 2 Chrysler front hubs, like you use for a van. They're only $16 nowadays if you get them without the toothed wheel for anti-lock brakes. They're kind of obsolete. They're about $40 if you get them with that sensor on them. Still not much. You get 2 sealed ball bearings, a malleable iron housing to mount it with, a 5-bolt flange like you put your wheel on. I mean, you got holes to bolt it down, and you got something to put your rotor on. What else could you ask for? Put one on either end, you're golden. And you can take a 2.5-ton van and cut a corner with it in town, and the wheels don't fold over. So it's plenty strong enough, and it's cheap enough. I bought a couple spares when I got it. Anyway, Wheatstone bridges will let you turn whatever the coil is doing into DC. Doesn't do much for you if you're trying to send AC to a 3-phase rectifier, because it's going to be coming in as DC. In fact, you probably wouldn't like it. But you can wire these rectifiers in series. You have the positive and negative DC coming out. Well, positive of this one goes to the negative of another one. You go right around the wheel and hook them all together, into a string, and then you only have 2 wires going to your batteries. And I'll guarantee, absolutely guarantee, that will make more electricity for the same amount of torque going in than any other way you can do it. I know people don't do it that way, but if you watch this channel, you'll find I do a lot of things other people don't do. It's just the way we roll around here. This is looking down on my bracket that holds my fan to the ceiling. Let's see. What did I do? This looks like a reasonable approach if you knew that there's 5 pairs of 2 bolts each coming through a 31-inch thick piece of concrete. And in this iteration, they had 5 plates on edge on one of the flanges for the motor, for the bearing housing. 2 holes each, 2 rods. These are separate up here. Being that these rods were designed to be double nutted, I could line that up in and out, loosen the bolt, slide it left, I could get it bolted to the ceiling. However, no, that's not either. Okay, now we need to find that. If we make it yellow, reason I wasn't finding it's not in that view. Yeah, there it is. Jump right out. Dog head, teeth in it, bite. Okay. The rim is now this the purple things on the top is the part that bolts the ceiling. They're just made longer till they butt up, and it gets 2 for the upper flange and 2 for the lower flange. 2 for the upper, 2 for the lower. Looks real similar. And the flanges they changed from 5 sides to 10 sides. Looks much nicer and easier to build because this center hole is bigger where it welds on, and that would just night and day different as far as assembly. We have the skirted things made and all the machine work for the bearing houses except for the grease fitting holes and a few things. This is cross sections of the stuff that makes up the bearing housing up here. It's got a big Timken bearing. That's the inner bearing of a tractor trailer. Turned out that it was about 30% the price of one either side of it because they make so many of them. Same brand, same quality, same construction, same materials, just a slightly different size. And you're making the housing, you pick the cheap bearing and buy a spare. And because this fan blade is pushing up, the air is trying to push the blade down, and that's why the big bearing's on the top. There's another Timken bearing down here because you have to have Timkens in pairs to keep them loaded into the race so it won't just walk out of the race. And there's a sleeve on here with 2 W nuts, around 2 3/4 shaft size at that point, with a locking tab that you bend over into one of 4 slots on the nut. Same thing at the bottom, except there's no locking nuts. It's the shaft has got a step in it because this bearing goes on from the other end. And there's also a spherical bearing down here that takes the radial loads. Things left to do are drill a hole through here where the 2 lines are, and put a grease fitting with a metal pipe up through the roof. And when you put grease into a Timken bearing, it climbs into the rollers and tries to get out the other side. So what you put in will flush out any surplus grease and put the fresh in place of it. And it will only take what it needs. A spherical, it's all trying to get back to the center. So if they come with a groove around them. So we're going to drill right into here, put the grease fit, and put it through the grease groove that's made for the grease groove. Fancy that. We're going to actually use something the way the manufacturer intended it. The reason for all these pieces is you have to slide things in from the end. like bearings have to go in and, you know, somehow get in there. The other is you can buy from Blue Metals, you can buy pieces of ship propellers and stuff that they've chopped up. Also, when they take new material, the first part that goes into the rolls when they're rolling or forging that material may have a different grain structure than the rest of the could be 80 feet long. So they'll take a 2-inch cut off the end to get it where it covers the entire diameter, and then they'll just lop off some amount, anywhere from 1 inch to about 7 inches. And at the other end, they take a cleanup cut, and whatever's left up there, they chop that off. So you get all kinds of different lengths available. It's hard to buy mild steel from those people. But this is these pieces are 4340 and 4140, and stainless steel 316, and one of them is aluminum up here. It holds a grease cap, not grease cap, but grease seal. All the weight's going that way. This one down here is stainless steel, and there's but like I say, these pieces are all made. Got them made in the Philippines, and he did a great job. The flange that the fan blades are going to bolt to, they bolt to these holes out here. These holes are drilled, but I'm only going to use the outer ones because the fan blade goes clear across. And this is a size E hub also, with a quick detachable hub on it. And the hubs are phased so that the open hole on the other one is here, so you can thread a bolt from that side into this. And this one, you'll be able to thread a bolt from this side into the hub on the other side. So when you tighten the bolts, it pulls all of it together. Just worked out that way. Some brands, these haven't got equal spacing. They only have 2 pusher holes, so the patterns are offset. I got lucky. I got some that the 6 holes are all, you know, phased the same amount. Anyway, the purpose of this video is draw your mess up with 1 phase, all the magnets. If you put the holes in your paper and you put the magnets on another piece with a pin in the middle, you can rotate that around and see what's going on to find out which ones are working for you. Positive to positive repels, and positive to negative attracts. Just like high school. You know, they call it laws of physics. It's not a suggestion. Suggestions, you have a little leeway. Physics, if it's a law of physics, yeah, no choice. It only works one way. Anyway, you can put 1 phase down, see what's happening. You know, if not as for insight into how these things are wired internally, Electro Noobs. N-O-O-B-S, Electro Noobs with an S on the end. He's got all kinds of electronic projects, and mostly all electronic, some mechanical. He's into drones and RC airplanes and motors in general. And he's got a real good explanation on how to drive motors and whether you want the MOSFETs or the other 2 choices I don't want to get into right now. IGBM or whatever it is, internal gate, they can carry a lot of amps. Those are available, but they're not as tried and true. They've been making them a lot of years, but an individual model has not been stable on production, so you haven't got a lot of track record. When Elon Musk built the cars, when he designed the cars, he basically knows who to hire. Really smart people who know industrial technology. He just, I don't know who his headhunter is, but he does a real good job. What they choose is tried and true parts, off-the-shelf parts, and they built some really nice stuff with it. His rocket is off-the-shelf parts except for the rocket motor. Everything else is off the shelf. But in his cars are AC. They got DC battery packs and three-phase brushless. These are brushless motors we're looking at. There's no brushes. It's a permanent magnet, brushless motor, permanent magnet. Rather than use the IG internal gated stuff, which you'd only need one of them per phase because they carry 1,000 amps if you buy them that size, they use MOSFETs, 042 package MOSFETs. There's 14 of them per phase running in parallel. That's a lot of redundancy. I don't know how many it actually takes, because I've got catalog listings on where each one can carry up to 300 amps, but at low voltage. The downfall of MOSFETs is voltage times amps, and that's watts. And all the way down, 2/3 down the data sheets, you've got heat dissipation. And that's the most watts that this thing can dissipate and survive. So if it's on all the time, that's the number you're looking for. If you need a lot of amps, you've got to have low volts. High volts, you need low amps. You can't violate that. And that's why you might have a motor that draws 6 amps and you've got a 300 amp capacity MOSFET driving it. Or you got 4 of them in parallel driving it, because you can't violate the thermal part of it. So draw your thing, count how many coils you got in each phase, and you're going to go in on one set, out on the other. So the number of coils in 2 phases is what you're trying to figure your wire for. There's a chart. It's going to have to, wait a minute, if I don't go too far, it won't do a redraw. And this chart's got 40 lines in it. This is getting down near the bigger stuff, but there's a lot of them going the other way. A lot of ceiling fans are like 35, AWG 35. So you pick a AWG wire gauge, ohms per 1,000 feet, amps that wire will carry, and the diameter of the wire. When you get to that point, you do your calculations for the one that you think is right, and then do one on either side of it. And if the one on the other side looks like it might be a close thing or maybe better, do one more. Get the one you think you really want to use in the middle and see what happens on either side. These wires come, by the way, in 16, 17, 18, 19, 20, 21, 22. There's some not drawn in here. I can zero in on it because I haven't bought the magnet wire yet. Oh, what I was going to tell you. If I take and I draw the shape of my coil, where is that? Make me look better. Say I draw the cross section of my coil, and I can make a scale wire, and I'm doing it this way because if you were using a ruler on a piece of paper, you would probably do it this way. Right to left. That wasn't very well placed. That was... Anyway, you can count how many wraps times your inches per wrap goes in the coil with different wire diameters. And of course, you may be running this as you know, a pair running. Excuse me. You know, he does what I tell it to do. I just don't tell it right. You may be running 2 wires to get the amp capacity you need. But the resistance, linear resistance only counts on one of however many you got. Because be carrying 2 wires, each carry half, and then that only gives you half the resistance for each one, so it adds up to the same thing. So if you're running parallel conductors, multiple conductors, then You can only count wraps on the on one. But especially if you have something like Google SketchUp or something like that, it's the 2D free version of Google SketchUp. You can draw stuff like this all day long. This is an array. It's so many wide, so many tall, and the spacing would be the diameter of the wire, and have at it. You can make an array and then draw your box around it and see how much of it cuts into. I got lucky here. That doesn't happen. Okay, I think we've beat to death how you get your wire size. Like I say, calculated for several different sizes. Your amps that one wire will carry times however many parallel wires you need to get to the kind of amps that you need. And the amps times volts is watts. It's 50. This is a 0.5 kilowatt generator, basically. And unless it goes, if it goes up over 48 volts, then it could be more than a 0.5 kilowatt. I don't know if that's big or small. But people that tell you they're getting 20 kilowatts and you look at the stator, maybe not. Okay, amps times conductors, total amps. Volts divided by the total amps gives you ohms. Ohms divided by the ohms per 1,000 feet of the magnet wire gives you it in feet. So this is the feet of wire you have to have. You're dispersing it amongst 10 coils in and 10 coils out. For me, that's 20 coils. Comes out in feet. Feet times 12 is inches. And the inches divided by the average in a turn gives you the number of wraps you have to have for each one. And of course, you got to remember you put 6 in up here, so you have to have 6 wires going into your coil winder. I recommend you run them through a wooden saw slot, like a hacksaw blade saw slot, to keep them all flat. If you get them all crossed over, one, you have a chance of damage. Insulation is higher, and the other, you can't get as much in there. In the 70s, when I was younger than I am today, we had slot cars, like 1/24th. So we would take 12-volt DC motors with brushes, and we'd rewind them to 3.7 volts and run them on 12. But on 12 volts, they spin up so fast, they throw a lot of air, plus the forward motion. Those cars were incredibly fast. 100, 115, 120 miles an hour, real miles per hour. And if they went off the track, it would just sweep up fragments. There wasn't nothing left. But when you got really into it, you had 4 ball bearings mounted, and you pulled your wire through that, and it made it square. And then you put that wire in there one lap at a time and adjusted it. And every layer you paint it with epoxy. And the idea is to get a bigger gauge of wire than you took off the armature, or more wraps. Either one makes more power. And then the lawyers started suing everybody over everything, and that went away, and the go-kart track went away, and the skating rink went away, and actually the movie theater went away in our town. It caught some kids doing the dirty down between the seats, and the police shut it down. The Boy Scouts went away. They just sued everything in our town. And of course, the lawyers didn't live in the town. They lived in D.C. or someplace. I don't think there's anything else that's totally interesting here, except my shopping list. Okay. This video has gone over, it's gone over 31 minutes. I might run it all together anyway. It doesn't make a great deal of difference because nobody watches this channel. I'm gonna title this channel so that somebody who's interested in wind turbines could actually find this video. But we're basically a concrete house building channel, one-of-a-kind houses, and how we do it, and how we make forms, and how we distribute electrical wiring through the house, and sub panels, and Just all kinds of stuff. And I'll throw in, once in a while, I'll throw 4 or 5 videos on making stitch and glue boats and how to design boats. There's surfboard sailboat and traditional Philippine fishing boat, hydroplane, houseboat, you know, just throw some videos up. I shut this off because the camera's still got power. I'm probably going to run a video on an enclosure for poultry. They call them schooners. You can drag it with your carabao and put them on new grass every once in a while, like every other day. Turkeys, chickens, doves, quail, goats, sheep. If you're trying to clear land, sheep or pigs, you know, sheep eat the grass to the dirt and it dies, and the pigs just root it up completely. Geese will also pour grass out of the ground if the ground's at least a bit damp. I'm not sure how geese taste. Turkey's good. Okay, y'all have a wonderful day, and thanks for watching at least the end of this video if you didn't watch any other part. Have a nice day. Bye.